My name is Favor Isakunobi now, and in this presentation, I will explain different analog modulation techniques using MATLAB. We will cover AM, GSB, SC, SSB, FM, and PM modulation, as well as several demodulation methods, and I will go through the code step by step and show the meaning of each signals. So first, I define the basic parameters that are shared by the modulation types. I choose a sample frequency of 50 kHz and I create a time vector that is milliseconds long. Then I set the message frequency to 200 Hz and the carrier frequency to 5 kHz. After that, I generate a simple sinusoidal message signals and cosine carrier signals. Now, I also create a small helper function called the IP. This applies a low pass filter with a cutoff frequency of twice the message frequency, and we'll use this later for modulation. Now, I generate standard AM, also called double sideband with carriers. The formula is 1 plus the message multiplied by the carrier. This produce carrier plus two symmetrical sidebands. Now, in GSB SC, that is the double sideband suppressed carrier. This is the simple, like this is how will I say? This is simple the message multiplied by the carrier, but without the added one. So, since there's no carrier terms, it is more power efficient but require coherent detection. Now, the SSB, which is a single sideband, is to generate this single sideband. I use the Hilbert transform to produce a 90-degree phase shifted version of the message. Then I combine the message and its Hilbert version to form the upper side band. Now this removes one of the sidebands and reduces bandwidth by half. So right now I have to develop detection for AM. So for standard AM, we can use envelope detection. We take the absolute value of the AM signals and the low pass filter rate. This gives us the original message back or the envelope of the wave. So that's for that. Then the coherent detection of the DSB SC, we must multiply the signals by the synchronized carrier. This shifts the base band back to zero frequency. So after low pass filtering, we cover the original message. Now the FM, which is narrowband FM, to generate this, we use a smaller modulation index beta. The phase of the carrier is slightly varied by the message, which produces a narrow spectral spread. So let's go to the Winband FM. For the Winband FM, I integrate the message numerically. The instantaneous phase become proportional to this integral. So this produces a true FM signal with large frequency deviation. So one way to modulate FM is to differentiate the signal. The derivative of the derivative of an FM signal has an amplitude that depends on the instantaneous frequency that I take the absolute value and the low pass filter rate, which covers the message. So another simple FM modulation method is to measure zero crossing. A higher frequency produces more zero crossing. The spacing between successive crossing is related to the message. So for PM, we directly vary the phase of the carrier using the message signal. With a small phase constant, this is a narrow band. Then for the wideband phase modulation, the wideband PM expression is the same, but the larger phase constant produce wider spectral spread. Now to demodulate PM, I extract the instantaneous phase using the Hilbert transform. Then I unwrap the phrase, remove drums, and differentiate it. Finally, I low pass filter to get back the message. And the final plot, in the last section, I plot six important signals. That is the AM, the GSP SC, the SSB, the narrowband FM, the narrowband PM, and the recovered PM signal. These plots help visualize the difference between the modulation types.